Okay, so let's take a look at today's lesson. Today's lesson is basically there's just one concept so far that we haven't covered. Today's lesson is applications. So the daily work that you're going to be doing is going to have a mixture of all different kinds of word problems from, the whole unit. But this particular concept we haven't talked about yet, so that's why we have just one slide today, and that is on angular acceleration. So let's talk about what acceleration is. Some of you may be or in physics, or maybe you've had physics, or you're going to have physics. We use acceleration, velocity, those kinds of things in calculus and physics. So what is acceleration? So let's say, I think we've been talking about speed. I think we're all comfortable with that, right? We've ridden in cars before. We know there's a speedometer. I mean, that's kind of a normal thing. But acceleration is just a little bit of a different concept, and not that anybody in here would ever do this, but let's say you were driving, okay, or maybe you watched this on TV. You saw a car on TV that was doing this. You're driving, like you hit the gas kind of hard, and it will pull you back. Well, the force that's pulling you back is acceleration, because you're accelerating rapidly. That pushes you back. So acceleration is the rate that you are driving. It's acceleration. So what we're going to look at today is angular acceleration. What would angular acceleration look like? Well, for example, let's say you've seen ceiling fans before. Maybe you have one in your house or somewhere in your house. So the ceiling fan, when it's off, it's just still, right? And then when you turn it on, it takes a little while to get up to speed. So the rate at which it gets up to speed would be the acceleration. You could, this would be kind of a fun thing. You could actually figure out your angular acceleration of your fan if you wanted to. Like if you're bored, Friday night, maybe tonight, you want to calculate that. That would be great. So let's talk about how we would calculate angular acceleration. So let's get the words down first. So angular acceleration, I think you kind of hopefully have a feel for what I'm talking about. It's the rate that the speed is changing, the rate that the speed is changing. So it's a rate the change in angular speed with respect to time. Now we're talking about angular acceleration. So at time 0, it's called initial angular speed. And in the example that I was explaining, like a ceiling fan, that would, if it was off, the initial angular speed would be 0, right? Because it's not moving anywhere. So many times you start with an initial angular speed of 0. Not always, but many times you do. So then we have at the end of time t, there's a final angular speed. So that kind of makes sense. You have a certain amount of time. The beginning you have a specific speed. The end you have a specific speed. So those concepts go into this formula. They're using this Greek letters alpha to designate angular acceleration, which is a fine Greek letter to use. So let's look at the formula. So you would take final angular speed minus initial angular speed. So I think of end minus beginning. And that end minus beginning is that concept is going to replay itself in many different kind of applications. So end angular speed minus beginning angular speed over the time that you're measuring, whatever the time is. So this is, I think, a fairly simple formula, and that's what we're going to be using. Now, there's two, typical units that we use for angular acceleration. One is radians per second squared. Notice with acceleration, it's not radians per second, it's radians per second squared. And then the other is revolutions. Sometimes they leave angular acceleration in revolutions per minute squared instead of an actual angular measure. Depending on what the word problem is asking for, you could use either. Or if it doesn't specify, you could use either one. So what I'd like to do is we're going to work this, we just have one example. We're going to work this one out in revolutions because it's in revolutions, and then we'll talk about what would we need to do to change it to radians per whatever the unit is. Alright, so we have a DVD, and this is kind of a thing, your DVD player is not on. There's no angular acceleration. You turn it on and then it starts moving. This particular DVD starts at rest, which means it's not moving, and increases to 600 revolutions per minute in 30 seconds. So pretty quickly it increases to 600 revolutions per minute, and wants to know what the angular acceleration of the chip is. So the first thing we'll look at is, we'll just leave it in revolutions. Okay, so with revolutions, we want our final angular speed, or in this case they're just giving it to us in revolutions, so 600 revolutions per minute. And I'm putting the units in here. Do you have to? No. I just kind of want to keep track of my units just so that I don't make a mistake. Maybe I would have to convert or something. I don't want to mess with that. So 600 revolutions per minute. My initial speed was 0 because it wasn't moving at all. So 0 revolutions per minute. And that was all over the time. Now the time they give us is in seconds, but these other measurements are in minutes. So we're going to have to fix one or the other. I think it'd probably be easier to fix the seconds, so I'm just going to fix that one. Well, 30 seconds would be a half of a minute, so I would put a half, or 0.5 down here. That's going to be our angular acceleration. So we work that out and we get 1200 revolutions per minute. Now let's look at why it's squared. Per minute squared. Okay, so there's our revolutions. 1200 revolutions per minute squared. Well, what if they didn't really want, and that's typical. See, it says revolutions per minute squared. That's a typical unit of measure. What if they wanted us to give that rate in radians per second squared, or radians per minute squared? Well, we would just convert our revolutions to radians, right? I mean, we've done that several times before, right? 1 revolution would be 2 pi radians. So we would simply multiply 1200 times 2 pi, and that would give us our radians. So if we do that, it gives us 7,539.822 radians per minute squared. And so if they wanted radians per minute, and see, probably if you look at the difference in those times, it's radians. They usually do radians per second or revolutions per minute. I think it probably has to do with just the size of the number. So the number is going to be larger with radians because we have to multiply it by 2 pi. So that's just a fairly large number, 7,500 versus 1,200. But that's basically it. That's the new concept that will be added to all your other applications. Are we okay with that? Any questions? Okay.